Hello, so today we will explain what if light suddenly slowed down, and we're gonna dive deep into the physics of this and what would happen exactly. We'll explain a lot of equations and what effects does the change of light happen to the real world. So, what does light speed slows down even mean? So in vacuum, the electromagnetic waves they propagate at c equals 1 pi, right? And where epsilon naught is vacuum permittivity and mu naught is vacuum permeability. So if light slows down, then from a c to a smaller value, let's say c dash, right, then something about mu naught and epsilon have also changed, so that will become dash and epsilon naught dash, right? And you can rewrite this into something like, let's just let's see, yeah, mu naught dash epsilon naught dash equals 1 pi squared, right? So now let's define the slowdown factor, right? So to do that, we just so k is obviously it's in between 0 and 1. Okay, so that's already like really huge statement. So vacuum itself changed its electromagnetic properties. So yeah, and there's a deeper issue than that. The deeper issue, it is changing a dimensional constant like c is tricky because you can hide it by changing units. What's physically meaningful are dimensionless constants, so especially the fine structure constant. The fine structure constant is the 4 pi epsilon naught Planck's constant and c. So this is the fine structure constant. So what this basically is that it measures the strength of the electromagnetic interaction. So like how strongly charged particles like electrons interact with each other. It basically controls the atom size and mostly the entirety of chemistry. Here this one is Planck's constant, right? And this is the elementary charge, which is the magnitude of electrons charge, right? Okay, so what about this? So here, if c changes anything, then everything changes, like the entire atoms, the spectrum, and basically the chemistry. Entire thing changes. So in this we will analyze two big cases. One is a naive literal change, and the other one is dimensionless. What's wrong with my pen? Okay, physics preserving sorry for the bad handwriting, change, right? So basically this one is less chaotic, and changes happen in a way that keeps the alpha and other dimensionless constants the same. Okay, so let's observe case 1. Okay, and only, so this basically is that only C suddenly becomes smaller. Basically speed of light reduces, so alpha changes basically, right? In this we can start with the Maxwell's wave equation, the electromagnetic waves, which is del squared mu naught epsilon naught, the double differentiation of the electric d squared. Yep. And so similarly for B, with the wave equation, V is 1 by mu naught epsilon naught under root, and this is basically C, right? So if suddenly mu naught epsilon naught jumps so that C becomes C dash, then every EM wave already in flight must obey the new propagation speed. So that produces a mismatch effect, similar to the waves hitting a boundary like refraction or reflection, except the boundary is in time rather than space, if that makes sense to you. So a simple way to picture it is the dispersion relation for light, which is the omega is, okay. So in here, if C changes suddenly, that allowed the omega k relationship, it changes instantly. So the omega and k relationship, right, it changes instantly if the C changes. So meaning frequencies and wavelengths, they can't both stay the same. And in time boundary problems, you typically get frequency conversion, and it's basically a time refraction effect. So the outgoing waves that split, the outgoing waves, right, they split into components with the shifted omega. So basically a sudden global change in the speed of light would generically create a burst of EM disturbance across the space. Not even propagation is safe. The spectrum entirely gets scrambled. And also in this we can also observe the special relativity. Oh, it blows up for the fast moving stuff. Right, so relativistic time dilation, which is it's basically 1 upon under root 1 minus square by light square, and the total energy is basically E equals, oh not this, gamma mc square, and from here momentum is gamma mv, right? So now imagine you have particles moving already, now imagine you already have particles already moving at some speed v, close to the old speed of light, okay? Then after the change, the new limit is c dash, which is kc, and there's a problem here. Let's go to the next page. The problem in that is some particles might have velocity greater than c dash, but in relativity, massive particles cannot have v greater than or equal to c dash. So something has to give, right? And there are two possibilities from this. One is the physics. I have to apply more pressure on the pen. The physics forbids the state. So universe must violently reconfigure the velocities and energies and everything. The other one is relativity itself changes, but then you're basically rewriting the fundamentals. So okay, let's keep the relativity and just replace c with c dash, okay? Then for the same v, a new Lorentz factor becomes like omega dash is 1 by, more pressure, 1 by under root 1 minus v squared by nu c square, and this would be something like 1 minus v square by k square c squared, right? And obviously for any v not equal to 0, and omega dash is obviously bigger, and sometimes if v is greater than or equal to c square, so if that happens, then the gamma is gamma. Did I say omega for this? No, it's gamma. Gamma dash is bigger. So basically the energy, the new energy, it becomes something like gamma dash m c equals gamma dash m k square c square, right? Even though c dash squared is equal to k square c square, is smaller, and gamma dash can become enormous, okay? So this means basically like many high energy particles like the cosmic rays, the accelerator particles, and particles in astrophysical jets, they will become inconsistent, or the force massive energy rebalancing, right? And in everyday life, if normal speeds like v is very less than c, it won't matter much. But space plus high energy astrophysics, they become instantly chaotic. And one more observation from this is atomic physics change because atomic physics change because of alpha change. And just recall the previous equation we wrote for this, the fine structure one. 4 pi epsilon naught, this one. So if only C drops to C dash, and C dash is obviously Kc, and E, the Planck's constant, and epsilon naught, they don't change, yeah. So then alpha dash is basically E squared by 4 pi epsilon naught Planck's C dash. Just a second, yeah, C dash, which gives 1 by. So this is a, so the new one, new alpha, it increases by 1 by k times, right? And in this, we can also see that the hydrogen energy levels So a standard result, like after solving a Schrodinger and Coulomb potential, that is the gross structure scales, like okay, E, it's approximately minus 1 by 2. Right. So with the new values that we got, we can simply, oh, this is gonna be long, me and the new speed by the new alpha by n squared, and this should give k squared c squared alpha by k whole squared by n squared, which is minus 1 by 2 me c squared alpha squared, you stay there, okay, alpha squared by n squared, right? So this is interesting. So in this simplified scaling, k, as you saw, k, it cancels each other, and so the gross hydrogen binding, it might look unchanged if epsilon naught truly didn't change independently, but careful there, that cancellation is hiding the real dependency in the Coulomb interaction, which contains the epsilon naught in the relativistic corrections. So the crazy thing about this is, if alpha increases too much, then atoms stop being stable in the usual way, and the relativistic stability constraint, it's not really important, but we're just going to cover that as well. So the relativistic stability constraint for heavy elements, relativistic electron speed scale, like right, and if z alpha is greater than or like approximately equal to 1, the electron speeds approach c, and then you get a supercritical behavior. I think since the Dirac equation issues, but yeah, they give a supercritical behavior. And if alpha approaches alpha dash, which is alpha by k, then for a given element, okay, the effective parameter, it becomes so if k is small enough, even the moderate z can push z alpha toward 1. That means the electron orbitals and the entire chemistry drastically change, and heavy atoms may behave completely different from what we know. Matter, as we know, may not even hold together in the same phases. So even if simple scalings cancel, the deeper structure of chemistry is not really safe, right? And we can observe also the gravity changes. Okay, so the Einstein coupling, it depends on C, right? So we can see the field equations of Einstein. The field equation goes something like V 8 by G by C. I think it's for T. Okay. So in this we can define kappa as this, right? So let's say C changes to C dash. C dash is basically Kc with the big G unchanged, right? Then we would have something like K dash equals G by Kc, for which technically gives you 1 by K4 kappa. Okay, this is kappa, it's not K. Okay, I just do this so that you know the difference. And where else here? This one, yeah, this one as well. Okay. And we can observe some things. So if the coupling becomes stronger by factor of 1 by 4k, 1 by k power 4, even a mild slowdown, it matters. So let's say if k is 0.5, okay, then k dash, not k, kappa dash is 16 times larger. And if k is 0.1, then kappa is very significantly larger, like more than 10,000 times large. So yeah, that's there. And if you look at the Schwarzschild's radius grows, they have weirdest names, I swear to God. right? Which is basically the black hole radius. Which is basically right. So okay, so what this means is basically objects become more black hole-ish because the radius of the event horizon, it expands, and this is very, very, very bad for the entire physics, the astrophysics, everything, because it changes everything. So this is there, okay, and the case 2 that we said, light slows down. Case 2, light slows down. Okay, we're not stopping it, let it slow down. But the dimensionless physics, it stays the same, okay? So if the universe changes in such a way that the dimensionless constants like alpha and all that, they stay fixed, then the local atomic physics can remain essentially identical. So to keep the alpha constant while C changes, something else must change too from this, okay? Okay. If let's say C decreases, okay? So you need to change, let's take the epsilon naught to change proportionality or E or anything, so that the total ratio, it stays the same, right? It should stay the same. So in that kind of scenario, chemistry might remain safe, and spectrum, this also might remain safe, and the things, every like day-to-day things, they scale with the same physics. So the rulers and clocks, which are made of atoms, they scale with the same physics, and you might not feel a change locally, but your the measuring devices, they change too, and the big observable change would come from cosmology. Let's say most of the changes that would happen in this case, cosmology. So how light travels over large distances basically, and maybe the horizon sizes, and basically the pre-universe processes, all that stuff. And this case is much less of a explosion, but it's more like a subtle but still profound though, okay? So what is the final result? So if suddenly universal drop C to Kc, not just light slows down, it implies either result A, which is where it's where the dimensional constant like alpha and all that, they don't stay fixed. So the Maxwell wave, so globally time boundary shifts, so there are EM disturbances and relativistic energy. The energy momentum relations, they also change instantly, so we have lots of electromagnetic disturbance, And then what else? No, not really electromagnetic. Oh, electromagnetic is in this one. Okay, my bad. And if this happens, then I think it's mostly just energy, chaos. And if there's also alpha increment of alpha, the chemistry, atom structure, likely everything changes, potentially catastrophic. And the gravity coupling scales like 1/, and the black hole radii scales like huge astrophysical disruption. Huge astrophysical disruption. Right? And let's say result B, the other one. Most literal and the boring one. So if C changes, dimensionless constant, and everything stays same, then nothing would happen, basically just long distance light travel times would change, and cosmological horizons and and gravitational scales, basically. So yeah, this is what gonna happen if light slows down, and it is pretty catastrophic, but it's pretty interesting how it influences these many things. And the beauty of we being able to calculate it is phenomenal. So yeah, that's it for this video, guys. I hope you have a great day, and let's hope light not to change its speed anytime soon. Alright then, goodbye.